Hi, everyone. My name is Gwendolyn Weston, and today I'm here to talk to you about type erasing. Now, your first reaction might be one of horror, because Swift is about type safety. Why would you want to erase a type? Or maybe your reaction is one more of confusion. What does it mean to erase a type? Or finally, maybe you're just asking yourself something even more basic. What is a type? And as I was researching this talk, I found myself surprisingly stumped by that question. It's weird how something that's so fundamental to our everyday coding practice was something that I couldn't even come up with a definition for off the top of my head. So in fact, I'm actually going to pause a bit right now and let you think about it. What is a type? All right, hopefully you have something in your head. Let's move on. The best definition that I found was one on Wikipedia, where basically the paraphrase is, a type is a classification that defines 1, a set of values, and 2, the legal operations on those values. So for example, the type int is all integers from -infinity to +infinity, and some legal operations on it are addition, multiplication, and the modulo operator. And this construct sounds pretty useful to the Swift compiler, right? Because with this constraint, we can figure out if setting something of type int to a string makes sense, or if calling the method indexOn on a dictionary actually works. Except not all types are created equal. In Swift, we can have these kind of unfinished types that the compiler isn't able to check the syntax for. So let's step back and actually talk about the difference between these two kinds of types, these concrete types and these abstract types. Concrete types are types that have an unambiguous implementation. Their methods are already filled out, and they can be instantiated directly. Another way to think about it is that concrete types are representations of data. They are rigid stacks of values that are passed around between objects in order to share information. So for example, here we have two concrete types. We have a concrete int, 42, and we have a concrete array with some strings in it. Then we have our abstract types, which are types with an incomplete implementation. They have placeholder types in their definition, and they can't be instantiated directly. And abstract types are representations of behavior. We use them to represent objects where their behavior is more important than the values they store. So for example, here we've defined an abstract type where it's a generic class of some type T and a generic struct of some type U. But if we try to instantiate them or declare them, the Swift compiler wouldn't let us. We can't instantiate some generic class T because it doesn't know what T is. Same thing with the struct. It can't instantiate a generic struct of type U because it doesn't know what U is either. So what do? How do we solve this? How do we make abstract types concrete so that we can use them in our code? This is where something called type reification comes in. Type reification is when we make an abstract type concrete by filling in its placeholder types. And that might sound a little confusing at first, but it's actually something we're all already familiar with. In fact, you probably use it quite often. And it's type parameters. So for example here, where we've defined this generic class T, when we instantiate it as a generic class of type string by passing in the string type parameter. Same thing with our struct. Even though we've declared it as a generic struct of type, some undefined type t, when we instantiate it, we pass in the int type parameter. And so both these lines now compile, and we can now instantiate our abstract types. Except there's one thing where we can't use type parameters, and that's protocols. Protocols do not have support currently in Swift in order to designate a type parameter when they are generic. So instead, what a generic protocol looks like is something like this. So here we have a generic protocol called Pokemon. And to the people who don't know what Pokemon are, let me give like a brief background. So Pokemon is little monsters that have elemental types such that they can battle each other. Anyway, so we have a protocol called Pokemon, and we have this generic type as designated by the type alias keyword Pokemon type. And we have one method on our protocol called attack, which takes this generic type, which takes an argument of this generic type, Pokemon type. Then underneath we have two classes that implement this protocol. We have Pikachu, where its attack moves are electric type, and we have Charmander, where its attack moves are fire type. And when we, ideally, we'd probably want to write some kind of battle logic between these Pokemon that looks something like this, where we declare something of type Pokemon, and then we attack based on some selected attack. In this code logic, it doesn't actually matter what type Pokemon we have chosen, nor does it matter what type the attack is. But the problem is, this code doesn't compile. Instead, we get this error that says, protocol Pokemon can only be used as a generic constraint because it has self or associated type requirements. Basically, it means that because Pokemon is an abstract type, we can't declare it. We can't instantiate it directly. The Swift compiler would not be able to understand how to reason about it. Instead, what we need is some way to tell the Swift compiler that we don't know what the implementation is up front, but we can guarantee that the implementation will make the generic type on this generic protocol concrete. So why don't we actually try to tell the Swift compiler that? Why don't we create this wrapper class called anyPokemon such that when you initialize it with this init method, it will only accept an instance that implements our Pokemon protocol, and two, where its Pokemon type matches the Pokemon type parameter that this anyPokemon wrapper class is initialized with. So using this wrapper class, we now can write code that looks like this. So the first line is we directly instantiate something of any type Pokemon by passing a Pikachu instance, where now P1 has the type anyPokemon electric because it's inferred from our Pikachu instance. Or alternatively, we can first declare something to be of anyPokemon type fire, and then later instantiate it by passing in a Charmander instance, which has the matching Pokemon type. Or, if we try to instantiate something that doesn't implement our Pokemon protocol, as shown in that third line with the Digimon, Swift won't allow this. The compiler will complain and say, this Digimon is not this doesn't implement the Pokemon protocol, you can't do this. Now, the downside is, whereas if we had initially just directly instantiated our Pikachu instance using the Pikachu initializer, it would be of type Pikachu. But now, because we have instantiated using this anyPokemon wrapper class, Pikachu is now instantiated as type anyPokemon electric. What has happened is that we've just erased type information. So this is what type erasure means. It's when we take this wrapper class, conventionally prefixed with the word any, in order to guarantee that you will instantiate an object that one implements our protocol and two fills out the generic type without necessarily having the implementation on hand. And honestly, I think that the name type erasure is a little confusing because the fact that we just lost type information isn't the solution. It's a symptom of the solution, but it's not the reason why it works. I think a better name would be something like type scaffolding, because what we've created is this construct in which our implementation will be guaranteed to fill in the required information. And another downside of type erasure is that we can't write code like this. We can't declare something to be any Pokemon of any object, and then later pass in a Pikachu instance in order to instantiate this object. The reason why is that Swift doesn't support covariance, which basically means that although the electric type should functionally be able to substitute for any object, Swift currently just doesn't support like replacing these with generic types. So there are some downsides to using type erasure in order to make our generic protocols concrete. One, there is a lot of boilerplate. And in fact, I didn't even show you all of the boilerplate code for the any Pokemon implementation. I'm going to leave that as an exercise to you all to figure out how to completely implement that any Pokemon wrapper. There are a lot of articles online. In fact, Hector has a really great article on his blog. I highly recommend it. You can also ask him about it later. And then second, we've just lost type information, right? The type erasure means that when we instantiate something with our wrapper, we don't actually know what specific implementation it is. We just know that it's something of type electric. It's something of type fire. And then finally, because we don't have covariance, we can't substitute like subtypes for a parent type. It kind of constricts the flexibility of our code. But maybe this will change. Already, Swift 2.2 has announced that the type alias keyword can also be used, can also be replaced by the associated type keyword. And a lot of people at Apple have already expressed that they want to support covariance and just automatically generate the boilerplate code of the any wrapper. So just to recap, because I know this was kind of like a whirlwind of type theory, we've learned, one, what is a type? In fact, I hope if there's one thing that you get from this talk, it's that you can now say you know what is a type. And I'm going to, again, pause and hope that you have a definition off the top of your brain. So what is a type? All right. I hope you were able to come up with something like that. Two, we've learned the two different kinds of types, these concrete and abstract types. Three, we've learned how to reify types using type parameters. And four, we've learned about type erasure. Anyway, thank you for listening.
Hey, Gwen, I loved your talk.
Thank you.
So I've seen that protocols with associated types example before, something that's kind of hard to deal with. Did you find any other examples of type erasure in everyday Swift code that was interesting to you?
It seems to mostly be when you have this generic type on a protocol. But some other example that someone pointed out to me is that sometimes you don't even need that generic type. Sometimes you don't even need that generic type on the function you're trying to call. So for example, if the function attack didn't even have Pokemon type, nonetheless, the Swift compiler would still complain when you try to call that, even though you don't need that type information up front. So people also just use type erasure to kind of get around that constraint. But so far, it's only kind of those two instances that I've seen it being used. Adam has a question over there.
Great talk. Not necessarily on types. Have you seen any nice solutions for doing this sort of thing with extensions? Because I know extensions cannot be genericized, but let's say, for example, like a gesture recognizer, you can have like a bunch of subclasses, but you can have added functionality attached to that sort of thing. Have you seen any solutions for that in your research?
No, I haven't, but that sounds really fascinating to look into.
This probably be more interesting for the crowd, but do you know what where Apple actually uses type erasure in the standard library?
It's like any sequence or any collection, I believe, is a type erase wrapper func.
Hi, Gwen. Great talk. Thank you so much. I'm kind of curious, apart from the example that you gave here, which was maybe a little bit easier and abstract for us to understand, is there like a project or a business problem that you came across which inspired you to kind of look into this research, or a problem that you were trying to solve where this helped you to accomplish a certain aspect of a project?
Yeah, so in a more like production environment, where I saw type erasure is my one of my old coworkers, Benji Enns. He has this open source library called ReSwift, I believe, and the idea is it follows Facebook's flux pattern or React pattern, one of the Facebook patterns, where it's like this unidirectional data flow, and you have a store that emits information, and then you have subscribers that listen to that information. And the way he used type erasure in that was that he defined the subscriber through a protocol called store subscriber, and then the type, the generic type was the store that it was listening to. And so then anything could become a store subscriber and could listen to information emitted from that store, if that answers your question.
Great talk, thank you. I was wondering if you knew where they stood. You mentioned the talk on the list about covariance and contravariance being like implemented in newer versions of Swift. Do you know where that stands, or is that going to be in 3.0 or?
No, I don't like have a definite timeline on it, but like where I'm getting that information from is one, Joe Groff tweeted being like, we don't support covariance yet, right? And this was last year. And also another old coworker like just kind of has a lot of contacts at Apple, and he was like, yeah, they're very keen on having support for covariance and all these things, because without it, it kind of makes type erasure quite limited to use.
Right.
Don't like type.
She don't like type.
What is best way to learn the type?
What
Best
is
way to
the best way to learn it?
learning type.
Oh. So I think your question is, what's the best way to learn how to use types? So write Swift, and what will happen, but there's more than that. What will happen is that with every single thing you try to do, the compiler will yell at you, and you won't know why, right? It seems to make sense to you, but it's going to be like, no, it's an optional. You need to make sure that it's not nil, or it's not an optional. You need to make sure it's not nil. It like kind of struggle through writing a Swift app, and it'll be like a trial by fire that will be a little painful, but at the end of it, you'll be like, I can write really type-safe code. And it only took me like 3 months of writing a very simple Swift app.
Thank you.
Yeah.
Good talk, thank you. I'm a Swift programmer. I love type. So,
So I have to speak in Japanese. Sorry. But type erasure. About the type erasure, could you please wrap up the talk about type erasure? Could you please elaborate on type erasure in one phrase or two?
Okay, so I think your question is, can I recap the definition of type erasure into something more concise. And this is something I actually struggled with a lot while writing this talk. I had like 4 different iterations of the definition. And each time I gave the talk to someone, they would kind of point out, be like, no, that's not quite correct. No, that's a little different. And honestly, I feel like the best definition that I got at the end of my road of preparing this talk is that type erasure is this design pattern where you have a wrapper class that has a constraint in the initializer method such that you can only initialize it with an instance of an implementation of the protocol you're trying to make concrete. But if anyone else has a better definition, please let me know. I would love to hear it. I mean, if it makes you feel better, it took me, so like I said, this boilerplate code is actually a lot more involved. This is a very like stripped down version of it. And it took me like a week of like looking at this code and reading through it line by line, like trying to understand it. And I think it took me like maybe at least 2 weeks before I even wrapped my head around, why would you do this? Why would you ever want to do this, right? So I kind of, this feels like a little bit of a cop-out, but I kind of feel like this is something you just have to struggle through until the end. You're like, oh, I made it. I'm stronger now, you know?
Okay, thank you. 後でまた質問させていただければと思います。
Thank you very much. I will come back to you to ask more questions.
He said he asked you later again.
Okay.
Thank you.
Okay.
Thanks so much, Wendy. Thanks so much, Wendy.
Thank you.
Thank you.